Good morning, everyone, and welcome to Highlands and Islands GoToWebinar platform. My name is Paul O'Brien, and I'm the Deep Wind Cluster Manager. This morning's webinar has been put together by the cluster's floating offshore wind subgroup. And before I hand over to Julia Rope from Fugro, who is one of the co-chairs of the subgroup, I'd just like to go over some of the features that we'll be using on the GoToWebinar system, particularly for the Q&A this morning. I'd also like to point out that we will be recording the session this morning and we'll be making the video and a PDF copy of the slide deck available on our website. Everyone registered for the webinar this morning will receive the link to this material when we publish it on our downloads page. There will be a question and answer session at the end of the presentations this morning, and you should use the questions box, which should appear on your right-hand side if it's a default. If you look at the selection of the grey boxes, there's an arrow. If you want to expand that particular answer and the chat, just click on the down or the arrow and it'll go to down and that'll expand it. If you could put your questions into the question box, and you can submit those questions at any time. If it's for a particular presenter, could you just proceed your question with "for" and the name of the presenter so we know that you want someone from one of the companies to actually answer it. So that's all from me at the moment, and I'd just like to hand over to Julia to kickstart this morning's webinar in earnest. Hi, Julia.
Thanks for that, Paul. Good morning and a very, very warm welcome to everyone online today. So today's webinar is about floating substations. We've got a trio of presenters for you from Linxon, Atkins and Hitachi ABB to talk to you about the floating offshore substation concept being developed jointly by the three companies. So to introduce our three speakers today, I've got a very short background about each one. So our first speaker will be Jose Restrepo from Linxon. Jose is a power system engineer. He's got a long-standing interest in the efficient integration of renewable energy and sustainable development. He's been involved in the integration of utility-scale renewable generation in Europe, North America, and the Middle East. Our second presenter today will be Sarah Marshall from Atkins. Sarah's a principal engineer. She's got 17 years of experience in multidisciplinary engineering and construction projects in the marine environment, and she's passionate about green energy generation and finding ways to harness natural resources for a sustainable future. And our third presenter of today will be Cesar Sois from Hitachi ABB. Cesar holds a Master's in Engineering in Power Plants and a Master's of Science in Physics, and has been working in the renewable energy sector since 2004. He's worked in a number of management positions and he's had global responsibilities. He's participated in several innovation projects that have helped develop technologies from early commercial stages. So without further ado, we'll get stuck into the presentation. I'll hand over to Jose.
Thanks, Julia. Thank you very much, everybody. I'd like to start by saying that it's a pleasure to have the chance to introduce this partnership in this webinar. It's been a few months of development in developing this partnership, and we're composed of three companies, as Julia just mentioned: Linxon, Atkins, and Hitachi ABB. Linxon, I'm here to represent Linxon, as Julia just gave a brief introduction about myself. I'm the engineering manager for Linxon, and I have a big passion for this idea, this concept, this floating concept. Linxon is an EPC company that we are currently involved in the development on offshore substations, onshore and offshore substations. And we have a share ownership. We're owned by SNC-Lavalin Atkins is one of our shareholders. The second shareholder is Hitachi ABB. So there is really a cohesive kind of direction in this group, in this partnership we're forming here. Sarah will be representing Atkins, and Cesar obviously will be representing Hitachi. From a Linxon perspective, we're an EPC company. We're the integrator of the solution. Our role in this partnership is the integration and the system design, and they're really the project drivers and how everything is glued together. Atkins will be bringing their knowledge in naval engineering and the selection of the floating substructure, while Cesar Hitachi ABB will be bringing their knowledge on the high voltage equipment and the technology readiness for the floating substation. So without further ado, I will continue with the presentation. The presenters will be in that order exactly. So this follows more or less the presenter order. So I would like to start with what are the objectives we're trying to accomplish here, and what are the key messages we want to pass on. And I would like to open with that. So from a technical perspective, the main driver is when we're developing a floating substation is to gain access to certain offshore sites for offshore wind, development of offshore wind, which are not technically suitable or economically suitable for fixed bottom solutions. Now, the second objective is to develop the floating concept that is in line with the current market needs and is also robust enough to be applicable or adapted to other emerging applications. So I'll spend a little bit of time of here what robustness means. Robustness need for us is that we spend a significant amount of time developing a solution that can be scaled very easily to different power levels, to different distances from shore, from different water depths, from different mid-ocean conditions. So we're going to present here an indicative design. You can see on the right-hand side, this is actually the top side of the substation, floating substation we developed. But in the design process, we take particular care to be able to retain the flexibility, robustness of the design, to be able to bring this idea to many different geographies in many different conditions. Now, the real objective, or the objective of this webinar, is to convey three messages. Is to say to the audience that the floating substation is a reality and is very soon to come. And we want to hear from the supply chain about readiness. We want to hear from the market. And third, we want to hear from developers. We want to hear from what projects are out there, what challenges are out there, and how we can address those challenges and how we can take this concept further. I will start with introducing a very, very high level very quickly what the context and application. At Linxon, we're coming from the electrical system integration. So I will present the context of the floating substation from the electrical point of view. So there are different ways that the floating substation emerges in applications for offshore wind. So the first one is, let's say this is topology, what we call topology A, is a direct connection of a wind farm to the onshore substation. And this is, let's say, the initial stages for any kind of development or technological development, where there is a proof of concept that the offshore wind farm can be connected onshore. But this is limited. This type of topology is highly limited by the amount of power, by the distance from shore, and this is not suitable for large scales. Now, when we move, our basis of our design is based on a topology B, which is a radial wind connection, which is the current model that is being applied to development of offshore wind farms at the moment, which is the substation is the aggregator of a large number of WTGs, and everything is collected. The voltage is stepped up and sent onshore. This is the advantage of this type of development, is that the number of stakeholders are limited, and there is a very well-known regulatory framework to actually deal with this type of project. Nevertheless, our concepts, our design concept also is applicable, is very easily applicable to other topologies. And I'm going to present two topologies here that are being currently explored in the industry. One of them is to use the offshore platform as an aggregator of offshore resources and as a balancing point for different offshore resources. And by offshore resources, I mean the offshore generation, but also potentially some offshore loads, such as the oil and gas fields. And you can hear in this situation, you can balance not only generation, you can balance the load, and in some cases, you can also have some kind of dispatching of the backup generation that is currently existing in offshore oil and gas fields. The third application, or the third topology, is what we call the truly an offshore grid. An offshore grid is different, let's say, parts of offshore aggregators being connected through a offshore transmission grid. Here, maybe it's a little bit faint, but you can see there is two connections between the two offshore substations. And what that really means is that the offshore grid becomes part of the transmission system. So you can either use the offshore grid to evacuate power from the offshore to the onshore, but you can also use it as a means to wheel power to the offshore grid. So you can relieve congestion or any kind of transmission limitation onshore. That's what we call the truly offshore grid. And this is even though the technology is known, the challenges, the regulatory challenges are a little bit higher. So our solution aims to tackle these different applications. Now, from the system integration point of view, there is, in the design process or the selection of the concept, there are many, many different moving pieces that we need to reconcile. So on the top left, we have what we call the technology readiness level of the different components. We have three major components in this, and the floating substation. One is the hull on the floating substructure. The other one is the electrical system design. And finally, we have the interfaces, because these substations are standalone. We have most notably the high voltage cable interface and the wind turbine interface. In terms of readiness, and Sarah will be talking more about this, the hull and the substructure is relatively mature. There exist very known commercial examples in the oil and gas industry. For the electrical system design, Cesar will be talking extensively about this, but there are currently solutions that are being used for this type of applications. And finally, the interfaces are the ones that are being pushed most notably recently for technological advancement, mostly the dynamic high voltage cables. We're trying to, in our design philosophy, we're trying to incorporate those requirements to be able to address the supply chain from the cable point of view, where our focus is mostly on the substation side. So the effect of the floating substructure, what does it really mean to have a floating substructure? So then the first thing is that the manufacturing, installation, and operation strategy may be completely different from a fixed bottom structure that you have for a floating structure. The way you install it, you operate it, you maintain it. Now, the payload weight and the payload interacts in a very complex way with the floating substructure, because the weight and the weight distribution changes the way the acceleration and the tilts are experienced by the platform. Not only that, that influences the equipment design, that in itself changes the weight and the withstand capabilities of the equipment. So it is an iterative process. It is a trial and error, which have more or less the main elements I've tried to capture here on the right hand of the slide. So on the top, when we started this exercise, we started with some local conditions, the mid-ocean water depths and soil conditions. We had some kind of looking at the different geographies in the world and what type of conditions we were expecting to find. The other overarching principle would be the power evacuation requirements. And finally, we started one of our overarching principles is the installation, operation, and maintenance strategy and constraints. And when we start going through that iterative design, we start initially with some payload characteristics. That is more or less all the three companies, or the three components. We sit down and say more or less what the payload should look like. And there is a preliminary sizing and concept selection, which really studies the way the electrical system, the topside electrical system, interacts with the floating substructure, and some analysis is carried out between the three participants to see if something can be optimized. And that process is repeated several times. Now here we also have considerations for the cable and the wind turbine interface, which are an important parameter that needs to be considered in the design of the floating substation. Here I'll be talking mostly about the techno-economical selection from the electrical point of view, pure electrical point of view, the top side of the payload, the high voltage equipment. So, and this is all typical electrical considerations, it is common for a fixed bottom as well as a floating solution, and they have to do, for example, one of the key elements is the power transfer capabilities of the existing cable technology to be able to transfer power as a function of the cable length. And at different voltages, you have different current carrying capabilities of the cables, but also you have different requirements for reactive compensation. And this is why you see these curves that are not exactly a straight line. Now, if you put that together along with the losses and you look at the levelized cost of energy or of the total investment, you can have, this is a very complex graph, but my point is that you may have different technologies that are competing and that need to be considered when looking at a project. So if you have, for example, here some AC investment cost that is here, that is, it grows, this is for the whole arrangement, the AC investment cost grows linearly as a function of the cable length, but it has some fixed number that is based on the cost of the terminal or the substations. You can also compare with the DC technology, for example, for long distances, where also the investment cost grows linearly, but the sunk investment cost in the substations is much higher than simple AC substations. The problem or the difference between AC and DC is that the AC losses are higher, and there is a point, there is a break-even point between 100 kilometers, could be even push to 120 kilometers. And that's fundamentally the comparison, the simplified comparison between AC and DC. Obviously, this needs to be overlapped with the capacity of the different cables to be able to see, to get a real picture of how this looks like. Now, when selecting the payload, we've come up with some sort of matrix where we have different power levels and different distances, and we have selected different characteristics for how the payload, the high voltage equipment needs to look like. So very short distances and very low power levels, we have a solution that it favors really an offshore substation. But as we start moving in power level higher and the distance, obviously the voltage and the technology starts to evolve. The voltage starts to increase, and at some point beyond 110 kilometers, it becomes obviously an HVDC solution. Our design, I'm going to show it later, our design is based on green line here. And this is where we've seen the immediate market needs to be more predominant at the moment. We think that the industry is going to move more into higher, bigger projects, maybe within 3 years or 4 years. But at the moment, the current developments are mainly focused on the green area here. And the green area is a 132 kV solution up to 300 megawatts. And this is our current solution is based on this at this level. Now, what is the effect of the floating substructure? So as I said before, there is a very complex interaction between the floating substructure and the weight. It doesn't mean that it's very hard to say that a bigger payload would not interact with the movement of the substructure that is better or worse. So it cannot be generalized that the objective of the design is to minimize the payload. It has to do with minimization of the payload, but very importantly about how you lay out the equipment in the substation to minimize those accelerations. So this is the solution we have presented, and really is very hard. It's very challenging to in 10-15 minutes to present all the process that went into selecting this concept. But we've come with, as I said before, with a solution that is around 300 megawatts or up to 300 megawatts, and rated voltages that are 150 kilovolts for the export cables, 60 kilovolts for the array cables, and it is suitable up to 70 kilometers for export cable. And in the selection of this layout, obviously it's an iterative process of finding the acceleration, the tilt, how to distribute the weights, the right dimensions, and obviously the equipment specifications for each one of the most critical equipment. And with this, I conclude my section of the talk, and I'll pass it on to Sarah. Thank you.
Hello, good morning, everybody, or good afternoon, good evening, depending on where and when you're watching this. Thank you for having me. Jose, if you're able to go on to the next slide, I'm going to do a whistle-stop tour to make sure that we've got enough time at the end for questions. So here I just want to say that we've been working in conjunction with this collaborative relationship, and I just wanted to summarize some of the contextual aspects of this floating versus fixed bottom substation. So the key design drivers that we need to take into consideration are fundamentally the environmental conditions. So that includes the water depth, the distance from shore, those metocean parameters, the bathymetry in terms of the geology and actual characteristics of the seabed itself. So obviously all of those things have to be taken into consideration, and I believe that we're going to present some of the effects of that in the next slides. So in terms of the motion characteristics, it's that key interaction between that topside payload and weight and how that interacts with the substructure itself and finding that optimized solution. So we're going to talk a little bit about how we believe we've got to that point and where we've got through that process and what kind of aspects of those motions we've considered and how it affects the design of the structure. Including the structure itself, if we're talking about floating, we have to talk about station keeping systems and the variations and the implications of those, and also the actual physical mechanical properties of those dynamic cables or any kind of other electrical infrastructure that's going to be attached to the floating platform. I've already mentioned distance from shore, but we've also considered that installation methodology that Jose mentioned earlier. And we want to make sure that it is as simple as possible to fabricate and suitable to install. So we've been considering all things like fabrication, construction, drafting and transportation and all of those things. So we're really trying to come up with a solution that really it's not in isolation, it's in collaboration and in engagement with the supply chain. So fundamentally, we need to have a design that is, as lower cost as possible and have that option for standardization and modularization, because that's where the commercial challenge will be met. And last but very much not least, we need to understand the consenting restrictions that's above and below the surface, and all of those factors will have an effect on the drive. Okay, so we've got a map of the world. I'm sure a lot of you are aware of the existing current projects that are in the water and potential future markets for projects and these locations, and where there's the longer term potential. So in order for us to start that iterative process, for us to understand how we needed to design it, we used our market knowledge and our understanding, and also the existing metocean conditions and water depths and all of the actual physical properties of those environments to decide on something that was as broadly as applicable as possible. Now, the site conditions we've chosen are actually in direct correlation with the east coast of the US, and it covers the North Sea as well, making sure that we're making a suitable design that is globally applicable, and we have to start somewhere. So on the right, you'll see some of the site conditions that this design has been suitable for. So in contrast to fixed structural design of offshore platforms, we really believe that the floating offshore design is much more capable of being optimized, and using that kind of optimization of the design process will actually improve the applicability and reduce the cost globally. Okay, so Jose has talked a lot about the topside power, and Atkins, we've designed a lot of fixed offshore structures, and we've designed a lot of floating offshore wind structures in terms of the demonstrators for the floating offshore wind market. But we're really being at the front end of driving down that design and fabrication cost, and we really understand the need for that standardization to reduce those costs and make it easy to fabricate. Traditionally, the topside weights have been completely driven by the range of transformer capacities on that footprint and the characteristics response that weight, that topside structure has on the substructure. In I guess simple terms, the greater the topside physical weight of the equipment, the more loading it will go into the substructure, and also the more steel will be required for the topside structural characteristics. So with that and the cost of steel, the push has been very much onto minimizing that steel topside and substructure weight. So it's been reducing that footprint down, both the topside section of it and also the footprint as it's connected down into those shallow water fixed applications. So with that comes its own challenges because of the motions that that heavy equipment on the top experiences kind of going down into that substructure. So in terms of floating, we actually can have a much lower and shallower footprint than our fixed counterparts. And what that does is it actually makes a better motion performance and dynamic behavior, reducing that need for that the additional structural steel weight effectively. So what we've done is we've come up with a solution that is a much lower and shallower, more spread out layout. And this actually improves the performance of the structure itself. It puts less stress into the substructure, and allows us to reduce the steel. So if we can go on to the next slide, please. I know I'm rattling through this, but I want to make sure that we get enough time in. So after we found our metocean conditions of we've chosen what sites conditions we're using and what our premise is, we need to look at concept select. And I'm sure all of you are aware that there are various different types of substructure that we can deal with, and we need to assess them all. And we did an internal and a collaborative assessment of of what would be the most suitable concept, what would be the most stable and hydrostatically best solution in terms of the inclination response to these dynamic net ocean conditions, and also the platform response to that loading, and also the weight on top of it and how it behaves in those net ocean conditions. You can see across the right, I realize it may be very small on your screen, but I'm sure people can zoom in at when they receive the findings. But basically, down the left we have of the table, we've got the 4-leg semi-submersible, we've got the barge and TLP and the spar. And we looked at all of them, and we really believe that the motion characteristics of the semi-submersible, because of the smaller water plane area and the adaptability of the substructure being able to increase its weight at a lower water level, actually make it a more stable and more optimizable solution for a greater set of locations. With that, we also need to think, as I mentioned before, about the footprint and the costs associated with that. So depending on that, the footprint of the moorings depends on the types of moorings. So with catenary, traditional catenary moorings, you're going to have a much larger footprint, whereas with the TLP, you're going to have a much smaller footprint. So you have much less impact on the seabed itself. So moving forward, I'm going to say that we've selected through the initial design has been catenary moorings, and I'll talk a bit more about the analysis that we've done on those. Just in the small picture in the side, we've got talking about the cable and that dynamic cable section, and we've had considerations as to whether it should be just free hanging, it should be a lazy wave, or have some sort of mid-water buoyancy support to protect it from any potential fatigue problems. So we also considered technology readiness levels of the equipment, and also location flexibility. So how tweakable, how tunable is it to be able to go between different geographic locations. And we really believe that our 4-leg semi-submersible option, as you can see by a nice green color, apologies if you're colorblind, but and the large number scoring on the side, but we really believe that this is the best solution to move forward with. So fundamentally, I'm just going to talk a little bit about the types of analysis that we've done. So we've built our structural models, and we've done an extensive amount of motions assessment and additional assessments that I'm going to move on to. But we have this parametric design methodology, which we've developed, and looking at those variable parameters of the column spacing. And so on the right, you'll see it looks like a very crude box, but actually what that is it's an incredibly clever parameterized design model that now enables us to alter things like the column spacing and the column width and breadth, and the pontoon length and depth and breadth, and the column depth, and the overall draft of the substructure in an incredibly quick time frame. And all of those final tweaks and adjustments and variable parameters provide us with those outputs that includes float out and displacement and actual structural stability of the structure in multiple conditions. So what we've done, and you can see in the bottom right, you can see without any numbers, I'm afraid, but we've basically been tuning the structure to make sure that it meets all the acceptable standard robust design criteria, but also making sure that we're tuning out anything that might cause complications in that dynamic response. So making sure that it doesn't hit any of those problematic RAOs at all, and making sure that all of those axes are considered, and we've managed to find a sweet spot for our design that meets that criteria. So it's just some quick overview of our stability assessments and our strength assessments. So when I mean stability assessments, we're talking about those transitionary capabilities. We've not just looked at that in situ once it's all moored and connected condition. We've looked at various different construction methodologies and drafts for potential creation from quaysides or float outs, and actually that in transit stability and during installation. So we've made sure that we've created a design and looked at all of those different variables and achieved that design in accordance with current DNV industry rules and regulations, but obviously including also the topside weights. So in terms of the strength assessment, the global strength assessment has been assessed for a 100-year return period sea states, and the deck strength has been considered. But as you can see from that, as I mentioned earlier, it's incredibly shallow. It's very, very flat, open structure. And this actually really does improve the structural efficiency and minimizes the steel weight of the structure. And we're currently looking at the local strength assessments for 100-year design pressures. I know I'm rattling through this. So much to cover. So we've also done, as part of the analysis, we've looked at the dynamic cable and also the mooring challenges aside. So you can look at, on the far right, almost like a plan view of what we're proposing with our catenary moorings. And we're looking at everything and all of those considerations. So I'm not going to read them out, but it is a very dynamic system, and we need to think about this in a very dynamic way. It's not just a one condition that we can analyze. We need to look at all those transitory stages. And I guess what I'd like to draw your attention to is the pictures on the bottom. So I know they're static. I'd love to have an animation for you, but I'm trying to explain the fact that if the platform is moving and it's at its maximum extension in terms of maximum mooring tension for whatever metocean conditions, you still have to design all of the dynamic cables and everything and the slack within that system to make sure that you minimize that offshore fatigue and vibration that it's going to experience in that dynamic condition. So just mentioned there in terms of mooring challenges at the current redundancy, but the mooring challenges associated with catenary moorings are predominantly in water that's less than 100 meters. So the floating applications we definitely think are suitable in 100 meters and less water applications, but that would then go back into another iteration of what would be the best mooring for this. So in this application, it's in the kind of 100-meter range is where we're sitting. So there are mooring challenges in shallower water for catenary moorings, but not for floating in general. So finally, I just wanted to conclude by saying, we've designed this and we've optimized it through parametric algorithms and using artificial intelligence to come up with the most scalable solution, basically looking at all of these alternative topside weights and water depths and varying metocean requirements. And we've got this one model that's linked to all of these key parameters that cascades through each stage of analysis, making that iterative process incredibly fast so that you can get to that solution, that optimal solution quicker. So we also really focused on minimizing the need for large construction through quayside integration of the topside. We don't want to use lots of really expensive installation vessels. We're trying to minimize that, and we want to provide safe access for crew transfer and maximize safe operating limits. And what that means is understanding that dynamic behavior of the substructure of the itself, mainly because we want to make sure our crew are safe if they have to visit it, so that they don't want to be on a very unstable platform trying to perform maintenance. So again, I say that we've made it as flat and as shallow as possible on the top side to accommodate as many multiple layouts as possible for adaptability and flexibility. And we're maximizing on that autonomous operation and remote monitoring condition assessment and trying to minimize that offshore intervention. And with that, I will conclude and I will pass you on to Cesar. Thank you very much.
Okay, thank you, Sarah. So first of all, good morning, good afternoon, everybody. It's a pleasure being today here with you and with our partners in order to share our floating substation development. A few words about Hitachi ABB. It's the pioneer technology leader with focus in power and digital technologies and advanced automation system as well. You see here that we are the company with the largest installed base in power systems. We have 4 different business units, grid automation with enterprise solutions in this business unit, grid integration, incorporating power quality and power consulting areas, high voltage products and transformers. We are present in almost 90 countries, 115 factories worldwide, 100 years working in this area and headquarters in Zurich. Few words about our, let's say, customers profile. The majority of them are utilities, despite that we also work with industry customers and transportation ones. The majority of our revenues comes from selling products. However, we also deliver services, software automation and systems, and we are pretty balanced in terms of, let's say, operations in the different geographies. So a few words about how we have structured our, let's say, presentation today for addressing or identifying what are the, let's say, the requirements for floating substations. We started by identifying the different demands and the typical electrical parameters. We assess these requirements. We thought how to address the challenge, and finally we can determine if we have a suitable portfolio for this application or not. We will see this in the following slides. Just a few words about the electrical parameters. Classical voltage level from wind turbines to floating substations is 3366 kilovolts. Mainly in offshore application, we are talking about 66. However, due to the increasing sizing of the power in the wind turbines, we could say that probably in the coming future, the 66 will be becoming 132, particularly due to the, let's say, additional length of the cables and increase of distance between one wind turbine and the other due to the power itself. For the evacuation power for the export cable, we typically talk about between 132 kV and 400. Due to the, let's say, sizing requirements in floating substation, we used to have GISs, so gas isolated switchgears, classical power transformer from 50 to 400 MVAs. And due, again, the length of the cable, etc., we need to have compensation devices, so such as FACs or shunt reactors or capacitor banks, together with some auxiliary services as gensets or battery for having backup power. So the challenges that we have identified in floating applications are a few, but we highlighted here the most relevant ones. For sure, the dynamic motions and acceleration is playing a relevant role here, and vibration together with corrosion as well. We need to design our products just for addressing these conditions. There is certain limitations in terms of space, weight, and ultimately in cost. So we need to ensure that our products are, let's say, the most compact one. In certain geographies, there are requisites of local content, so we need to address this challenge as well. And there are some requirements in terms of efficiency of the products. Okay, so we, let's say, address the different requirements just by designing and ensure that our equipment, electrical equipment, are supporting the accelerations and vibrations. We need to ensure that our products and solutions are cost effective. It is being done through modularization and standardization of the products associated to floating substations. We also have to contemplate what would be the, let's say, execution and erection processes, not only in the yard, but also we need to ensure that the equipment are supporting the mooring and the transportation to the final location. Also needs to be, as we said before, competitive, and this will impact the LCOE. So we need to optimize these values just by having a reduction of LCOE, and to plan and address how we will perform the commissioning once the equipment and the floating substation will be located in the final place. So we consider, we have a number of lessons learned because we have a let's say, relevant footprint of more than 90 projects, floating ones in oil and gas industry, in which our products have been installed, typically in oil and gas platform and FPSOs. We also have an experience in floating projects, only wind turbines ones, not with floating substations, in order to get some, let's say, experience on that. So we have participated in a number of them, and also for the, let's say, marine conditions, etc., due to the, let's say, footprint that we already have in wind offshore, not floating, we have understood as part of the challenges. However, in order to, let's say, have a 300 degrees view, we believe that the stakeholders' engagement is becoming pretty relevant. That's why we have had an interaction with floater designers, so yards, EPCIs, and for sure developers and IPPs, in order to have the, let's say, the feedback from different parties, just to ensure that our products are suitable. Okay, so how we address the challenge, right? We establish a kind of action plan in our organization just to ensure that our products are suitable for floating with substations. We started by participating in a number of floating substation demonstration projects. We have performed different studies with internal and external stakeholders in order to ensure that our equipment will support the main demands in terms of mechanical strength and motions, etc. However, depending on the final location of and the characteristics of the geography in which the floating substation will be located, perhaps in some cases we will need to do additional studies. Due to our global footprint, we are able to ensure that we can contribute to fulfill the requirements when it comes to local content, and also our global footprint is helping us to be, let's say, or have an optimum in supply chain. Digital solutions can also help to better benefits to our customers, and we will see this afterwards. So then we can certify that we have suitable portfolio for floating applications, fulfilling all the requirements in terms of voltages and power requirements. We have developed a particularly part of our portfolio for being, as I said before, suitable for floating applications, just by, let's say, redesigning certain parts of our products to ensure this fulfillment, particularly again when it comes to the mechanical strength and vibrations of the products. We can say that we have a good adapted industrial solutions, standardized and ready for being developed in the market. So digitalization, this is also an area that will contribute to have a competitive products in floating wind, in floating substations by, let's say, for instance, having, let's say, important relevancy in safety and security, because using digitalization concept, we are able to minimize the execution times. We are able to minimize the operations on site when the platform is located in the final location. By having our advanced enterprises software, we are able to reduce the number of outages that will impact positively in the LCOE values due to our, let's say, a concept of operation and maintenance through our enterprise solution as well, where we are able to maximize the benefits of these enterprise softwares by reducing the number of hours doing maintenance on site, etc. So, as I said before, digitalization is playing a key role in this kind of applications. So the last one, all in all, just a sort of conclusions, we can determine that we have a fixed for purpose and we are ready for a floating substation application with our products by having modular and scalable products that will contribute also to be very competitive due to this modularization and standardization. By using digitalization, we are able to shorten the execution period. We are very flexible in terms of voltages and power when it comes to step-up transformers. And also we have a complete and comprehensive portfolio of compensation devices ready for being deployed in floating applications, particularly as those that we already mentioned as shunt reactors or FACS systems and gensets, etc. And last but not least, we are very, let's say, we pay a lot of attention and time from the operational perspective, just to bring additional value to our customers by having solutions that will help the customers to minimize the LCOE, shorten lead times due to our global footprint, as I already said, etc. So that's all from my side. I hope that this have been interesting for you. I think that we can close here the presentation. We can go to the Q&A.
Thank you, Cesar, and thank you to Jose and Sarah as well. It's clear that a huge amount of work has gone into this project and a huge amount of transferable industry knowledge as well. So we've got a few minutes for Q&A. There's quite a lot of questions. So I'll dive straight in with a question for Jose. So, have you considered integrating some of the electrical plant onto the wind turbine platform itself? As wind turbines increase in size, the wind turbine platform will become larger, and hence some electrical plant can be located on the external platform or in the tower. Certainly 132 kV is likely to be possible. What are your thoughts on this, Jose?
Yeah, we actually have thought very, very much about it. And if you try to do that, you're raising other challenges. So I think it's an excellent idea, by the way. It really deserves to think about it. The challenge that we found is that you start running into issues about reliability, for example, because all of a sudden you have a very long string of turbines connected through a single array feeder. The number of high voltage dynamic joints increases, so that complicates things from a technical point of view and reduces reliability. Things such as the grounding, the electrical grounding, of the design of the grounding system is also a consideration that is very important for the offshore substation, and so how you transfer that into a distributed kind of 132 kV network. There are many things that need to be considered. There is the telecom requirements, how you're going to address those. You're going to distribute the telecom functionality across all the turbines. Same thing with the SCADA. There are many systems that are in the substation for a large power development, and you have to find solutions how to transfer those to the actual turbine, each one of the turbines. So I think it's an excellent idea. I think is what I would say is not, for me at least, it's not straightforward. It's worth looking into it, but it also raises some technical challenges that are not evident to solve right away.
Okay, thanks very much, Jose. Okay, I'm going to move on to a question from Sarah, and this is one that I've seen come up quite a few times in the work that we do. It's on marine growth. So, has the effect of marine growth been taken into consideration for the performance of the system over time?
So the short answer is, yeah, no, it's a really important question. And yes, marine growth has been taken into consideration for that kind of the idea of that over a long period of time being in situ and it building up. So the answer is that we would simply adjust the ballast of the structure, so change the actual system. And that's the beauty of the semi-sub design, because it can be adjusted for that very case. So yes, it has been considered. Thank you.
Okay, brilliant. Another question for Jose. On a fixed bottom structure, you would normally earth the power system through the legs or the pilings. How do you earth a floating offshore substation?
There are options. Our preferred option will go through the moorings at the moment. That's the short answer, but there are options. You can also try to do somehow with the cable. But yeah, at the moment, we're envisioning the mooring as the main option.
We've got a question on excursion, which I assume is relating to how much everything's going to move. So what's the maximum excursion expected?
I think that's for Sarah.
So at the moment, it's one of those solutions that we're trying to create that mooring for, and I'm not really willing to disclose the actual specifics of the design at this stage.
Okay, thanks, Sarah. Right, I think I've got time for about one more question. So let's talk about engagement with the supply chain. So what type of engagement or what level of engagement have you had with the cable suppliers to check what state-of-the-art cables on the market? So 132 kV or higher voltage dynamic cables?
I can answer that to the best of my ability. So it's obviously has been recognized as one of the technology challenges that need to be taken. Our philosophy is we're interested in designing the substation that can work with the current available supply chain. In that, we have had to have a lot of surveys and discussions with the cable suppliers to understand where they are. We want to make our design fully compatible with the existing supply chain. That was our objective. Now, what different developments by the different cable suppliers, those are, information that I cannot disclose. But we have, our objective is to have a floating substation that is compatible with the state-of-the-art technology on high voltage cables.
Great, thank you very much. We've got loads more questions, but not enough time. So I'm going to say a big thank you and hand back to Paul to close today's webinar.
Thank you, Julia. Hello again, everyone. Paul O'Brien here. I would just like to thank everyone for participating in the Deep Wind webinar this morning. And a special thank you to our presenters, Jose, Sarah, and Cesar, and well done to our anchor, Julia. Sorry for the floating wind pun there, couldn't resist it. Just want to give a quick plug for our webinar on the 12th of November, which is coming from Deep Wind member Floating Energy Alliance, who will be actually talking about their forward plans for the supply chain opportunity linked to the Scotland leasing round. So contact us if you would like an invite. I have just pasted my email address into the chat. So if you want to take a note or just copy it, you can contact us to ask if you would like to be invited to that. Okay, so I hope you agree that this morning's floating substation topic has proved to be stimulating, thought-provoking for this webinar, and we look forward to welcoming you to our next webinar. We will try to answer individually questions that were unanswered so far. We'll get the team to have a look at them and see what they can come up with and come back to you on that. So it's goodbye from all the team at Deep Wind, and enjoy the rest of your day. Goodbye.
Thank you very much.